thank you very much for the help, and thanks, Felipe, for the invitation. I'm going to talk about, well, the title, this is not Recife, there are no reefs. So, and I hope this doesn't.
You got the message because of the recording.
Yeah, the problem is that this somehow locks my.
Oh.
Yeah, this works. So okay. I'm going to talk about the work I put out in the archive. Well, we put out in the archive last 2 months. It's a joint work with João Paulo, who was my PhD student. He just graduated, and Mauricio Richards from UFABC in São Paulo. Wonderful. I was afraid this was going to happen.
Oh.
Sorry about that. Okay. Wonderful. Okay. Great. Right. So this is a basic outline. I'm going to apologize in advance because
the screen share stopped. I'm sorry.
That's great. Just I guess I have to go out. Share again. And then, yeah, I know. I don't care. Yeah, please give me control. All right.
Sorry.
So, is it all right now?
Yes.
Okay.
Good.
I'm going to apologize in advance because I understand that most of you have a gravitational background, and I'll be talking about stuff that usually people talk about in field theory. I'll be brief about that and try to give an outline of what is the message by the end of it. And I'm going to, well, discuss the results. Hopefully this will be most of the time I've spent, and give some analogies that hopefully will help you give some context to the results. So, all right. So I guess this is pretty much something preached to the choir, because pretty much everybody knows here, but the problem of linear perturbations of geometries is, well known. I don't need to motivate anyone here about the importance of this problem, but the essence is the same of classical mechanics. You have some system, you perturb the system, and you see what is the response. Well, the nice subtlety, at least for genetic case from gravitation, is that you cannot turn gravity off. So there is always interactions here. What does that mean? It means that not only you're going to have a response in form of the linear perturbations of some modes, or some like modes of pipes or of an organ or some other instrument, but you're also going to have decay time. And this is built in. You don't need to have any additional structure for that. Okay. So the particular problem that we are going to worry about is the massive scalar field in this case in Kerr backgrounds. So just as a disclaimer, this is 4-dimensional Kerr, generically rotating, no ADS, no funny business, just regular Kerr background. But the field I'm considering is not the scalar field or massless scalar field or some higher speed field. It's just the old Klein-Gordon field with some definite mass, mu. And it's been, I mean, it's an old result, a classical result, that the Klein-Gordon equation can actually be separated in this background. And you have some ansatz like that for the solution. And you can separate the wave equation into two ordinary differential equations. And they are written like that. The parameters are usual. Mu is the mass of the field. Omega is the frequency of the perturbation. M is the angular momentum. Lambda is the separation constant. I'm going to talk more about that soon. And what else? Yeah. Uppercase M is the mass of the black hole, and A is the rotation parameter, J over M. So this is pretty much as usual. It will be useful for me to remember that this function here, delta, has zeros at the horizons of the black hole. But apart from that, I guess this is pretty much known from anybody here, so I don't need to dwell too much time on that. So both of the equations that I have from the mathematical point of view, they are instances of what is called the confluent-Horn equation. The confluent-Horn equation is an equation, classical complex analysis. It's an equation that has some structure And we're going to exploit this structure. So let me start with the beginning. First of all, this equation has points, singular points that z equals 0, z equals t, and it's hidden here, but you can uncover it has some odd point at z equals infinity. And what does that mean? Well, it means the solutions of this equation, they have some polynomial singularity at 0, at t, but has an exponential singularity at infinity. This is a bit not unexpected because, as you probably know, the wave equation, as you come close to infinity, behaves like a wave. So you have some oscillatory behavior. So in my mathematical way of saying this is equivalent to the exponential function. And you have some polynomial decay near the outer horizon. Usually you phrase that in terms of the tortoise coordinate and it becomes an exponential, but in my case, this will not be interesting. I'll just write this in terms of the coordinate itself. And also near the inner horizon, the Cauchy horizon, you also have the same behavior. In general, of course. I mean, you can deal with extremal limits where the Cauchy horizon comes closer to the event horizon. I'll talk more about that soon. All right. So what is the problem actually? I gave you the equation. What is the problem that you want to solve the equation? Well, to specify a solution, you need boundary conditions. I guess everybody knows that. And the two equations are very similar, at least for the problem that I want to solve. The angular equation, which is this first one that I wrote down here, this for s. I mean, I'm writing that in terms of this coordinate. This equation is close relative of the usual Legendre equation that you find when you're studying spherical harmonics in usual quantum mechanics. It's a bit more complicated than that, but the problem that you want to solve is basically you want to find solutions of this equation which are regular both at the North Pole and at the South Pole. Here you basically have the same thing. You want to find solutions for S that are regular when u equals 1 means North Pole and u equals -1 meaning South Pole. So you can see, for instance, that you have problems when u equals +or -1 because terms like this and this term, they diverge. So finding equation that, find a solution that is regular at both ends places constraints on this constant here, separation constant, and this is how you find the eigenvalues. So I trust this is nothing really new for anybody. So this is a Sturm-Liouville problem, classical Sturm-Liouville problem. And the solution is that by requiring these non-local boundary conditions, you restrict the parameters that you want to consider in the equation. Well, what about the radial equation? The radial equation has another structure. You may want to study something else, like gray body factors or things like that. I'd be particularly interested in quasi-normal mode, like I wrote in the first slide. And what it transpires from a little inspection is that this is also kind of Sturm-Liouville problem. It's also kind of boundary problem, meaning that you want to find solutions which are purely ingoing near the outer horizon and purely outgoing near infinity. So you don't have any flux of energy inside your space. And this places, requires a solution that doesn't mix behavior. They have this behavior at r equals r plus, the event horizon, and also at r equals infinity. So that also places restrictions on the parameters that you have in the equation. And the only three parameters that you have in the equation at this point is the frequency. So you're going to find a discrete set of symmetries, frequencies, exactly in analog how you find a discrete set of eigenvalues in the angular equation. What is the catch? The catch is that what you call the potential in this case is much more complicated. So you have all this stuff here, and not only it's more complicated, it's also imaginary. So you see that there are some blatantly imaginary points here, and also be imaginary if the square root involves negative numbers. So if the mass is low enough. So the problem, although the problem can be, you can phrase that problem as a Sturm-Liouville problem, you cannot use the usual Sturm-Liouville analysis to solve it. What is the usual method that you want to solve it? This is also known, I think, for everybody here. You find what the mathematicians, you propose what the mathematicians called the flow case solutions. These are solutions of the Hoyle equation, genetic solutions of the Hoyle equation, but they are not analytic, at least not near zero. You see, this is a Laurent expansion here. And if you look up the books on complex analysis, you're going to find that this may not converge near zero, probably won't. But in this case, you assume that's going to converge inside some annulus whose linear radius is actually more than this t, which you should think of as the outer horizon, and less than one. One here is some sort of it's actually a technical requisition. You can push this forward by some other means up to infinity. But you want the solution basically to be analytic in here. If the solution is analytic in here, there's another way to characterize the problem, because you see there is a term in front of this analytic term that's non-analytic. So this, as you go around the annulus, is going to pick up a phase. And the phase will depend on the new parameter, sigma, that you have to propose. Finding sigma is not easy. You have to work a lot. But there is a way to do that. You basically substitute these ansatz back in the equation, and you solve this three-term recurrence equation by means of this continued fraction. And this is, for the particular case, this is what's called the lever method. You place some specific value of sigma that guarantees that the solution will have the desired behavior, and then you crank up the machine. You basically, I guess everybody probably read a paper where somebody used this method. I'm going to refer to this continued fraction equation a lot. So I just want to at this point, I just want to tell you that this equation, however complicated, is some implicit relation between the parameters on the differential equation, which I'm calling c, t, and theta, and this parameter I had to introduce, sigma. Okay, so this finds you or resolves to you implicitly this parameter sigma that I have to find. I'll talk more about sigma so you understand why I have to define it. For a small t, I guess you're going to see that this is basically known. You can write expansions for this easily. So expansion begins with the term that diverges when t goes to zero, but otherwise it's analytic in t. This is actually it's the reverse map. I want to study the parameter c in the equation, just that you don't get lost in so many different definitions. C is this parameter here. It's usually called accessory parameter in mathematical language. And it's easier actually, instead of defining sigma as a function of c, to define c as a function of c. So you go forward and then you propose an expression like that. And the parameter that you have to read up in the equations, they actually have a nice interpretation. So I'm going to talk about them a little bit. The singularity at the inner horizon has this form. The singularity at the outer horizon has this form. And the singularity at infinity has this form. So these parameters thetas are known once you know the frequency. I'm writing them in a way that maybe is slightly mysterious, but for me, this makes a lot of sense. T plus is the temperature of the black hole, and this is the angular velocity of the horizon. So if you use I think this is called effective frequency or something like that. Anyway, I call this entropy. This is the variation of entropy that the black hole and the black hole absorbs the quantum energy omega and angular momentum m. So, and don't go quoting on me that this is also entropy. I don't know what this is. This is the inner horizon. I don't know anything about the inner horizon. Well, so what's the catch? What's new? Well, the equation that I just showed you appears in another context. And just to give you a flavor of what it is, I have to spend, I hope, less than 15 minutes on conformal field theories. If you want just to nod off, have some, it's a perfect time to do that. I'll recap by the end of it. So there is something called in field theory, it's a two-dimensional field theory. It's very simple, called Liouville field theory. It serves as a model of classical gravity, but I'm not going to talk about that here. What is important to me is that this field theory is an example of what's called a conformal field theory, which you've probably heard about. And conformal field theories have the special operators, which are called primary operators. and which transform nicely under these conformal transformations. And because of conformal symmetry, you can actually find or integrate the word identities that this correlation function satisfy and determine the 2- and 3-point functions exactly. So lots of work is done for you by just the symmetry. Well, you can think of this 2-point function. This 2-point function is 0 when this scaling dimension of each of the operators is different, and the 3-point function in general is not 0. You have some constants here which are called structure constants. You can think of this actually as defining a inner product in an algebra of operators, and this defining multiplication in the algebra of operators. So 2 and 3 points are fine. What about 4-point functions? Well, 4-point functions, they are a bit more complicated, but you can use the symmetry to basically relate them to 3-point functions by doing what's called a partial wave operator. You basically consider generic 4-point function processes, and you split those 4-point processes into intermediate states. And these intermediate states, they can be computed using the Virasoro algebra in 2 dimensions. This is in 2 dimensions, by the way. It's a lot of work. You don't need to know about this, but the problem is that there are ways to compute this 4-point functions, also based on the conformal transformations. And what does that have to do with anything? Well, there is a piece of information from conformal field theories is that there are representations. So there are some intermediate states in which you have a finite number of states. So you begin with the first, what's called the primary state, so the lowest level state, and then you begin populating. Then at some point you reach a null state, a state with 0 norm. Usually states of 0 norm, they are they should decouple in sensible theories, because if they have 0 norm, they should be orthogonal to anything, to everything. This is what happens, for instance, in electrodynamics. You have 0 norm states, and the whole work that you have to do with group tabloid, FADEF, Popov, what have you, is to decouple these null states with longitudinal and scalar polarizations out of the spectrum. In the end, if you work right, you get only 2 polarizations as you should. Here, these states, they should also decouple. And the decoupling of these states, so that means that any inner product of these states with null states with physical states has to use 0, can be cast in terms of this differential equation. Well, differential equations are a bit closer to what we want. I just want to tell you that this differential equation reduces to the confluent Hoyne equation in a particular limit. So what's the catch? Well, you see that there is a term here, this term, that has this partial derivative with respect to the parameters, that's similar to this term here, C, that I used this method due to lever to compute. So whatever you have there, this partial derivative could in principle be computed also from conformal field theory. And this is exactly what I've done. Well, there's about how this multiplication that I talked to you about, the 3-point functions, it selects solutions with particular properties. I'm not going to talk too much about that. It's not particularly relevant. But the point is that you can have a limit in which the equation that I just wrote, the equation that I wrote in the last slide, this partial differential equation, second line, turns into this ordinary differential equation. This is a sort of decoupling limit in which you take the conformal dimensions of these operators to be very large numbers and keep this finite. So that means that you basically can understand the correlation function as the fluctuations due to this term in some heavy background. Let's go to those steps. And this is exactly how you do this. You choose those terms to mimic what you have in the black hole, and then you can compute this this function W here. It has a name, and you find that the C parameter that I have in the field before can be computed using this W. Now, remember the sigma that I wrote to you, told you about? Yeah, the sigma also is a natural variable of this function. So if I know this function, I can also know the map between sigma and C. And there are many ways actually to compute this function. I'm not going to go into that, but this is also something that I have to talk about because active area of research in mathematical physics, people from Marcos Marinho, people from Stony Brook, people from CISA, people from TU, and I would like to include myself in the picture, but yeah, we are in this. So there are many ways to do that, things that are important from string theory and field theory that we can discuss later if you are interested. What is important about this sigma parameter? Well, the sigma parameter tells me how the solution behaves as I go around the complex plane. Remember that for the radial equation, I had some singular points at 0, t, and infinity. I'm talking about some specialized version here, which is actually simpler to discuss what is going on. Because of this, the Frobenius solution, you know, the Frobenius solution has a leading term that you get by solving the initial equation. I hope it's here somewhere, like this. And then you find a series. Of course, you hope that the series is going to converge, but if the series converges, it converges to an analytic function. This leading part here is not analytic. That means that if I go around t, this will pick up a phase proportional to theta. Okay? The analytic part doesn't. Well, the Floquet solution also has the same behavior. If this converges to an analytic point, if I go around the complex plane, this will pick up a phase, but this one. So you see here, sigma parameter controls which kind of phase I pick up as I go around this path. In this case, it has to be inside the annulus because there is where the series converge. So in general, the sigma parameter is related to how which kind of phase I get if I go around the analytical plane, the Z plane like this, to relate to sigma. If you have more singularities, you can have some more parameters. This one, for instance, will be related to the parameter that I get by going around the solution that's singular at 1 and t, or at infinity and t, and so on and so forth. This space can be parameterized. You have some nice parameterization, and it's even suitable for us will be the space of such phases, I should say. It's parameterized, and the nice parameterization is of sigma and this canonically conjugated variable eta. That's obtained in exactly this form. So if you remember your classical mechanics, you can see that this function here has a sort of interpretation as a generation of canonical transformations between those variables. And this is exactly what these people in mathematics that I'm visiting are interested in. We are not interested in mathematics, we are interested in physics. So the message that I want to convey to you, and my 15 minutes is almost up, so I better rush. That for each of these ordinary differential equations that show up in this perturbation business, I have some field theory that I can use to compute the sigma parameter, and then you see in a minute, I can use to compute the quasi-normal modes. For the in and outer horizons, they are basically the usual parameters that I'll show you. There is some B parameter in this case, it doesn't have, in the gravitational sense, it doesn't have any interpretation. Funny business is that if you have a real frequency, which of course it's a problem that we are not interested, but suppose that you have a real frequency, this parameter here leads to a primary operator which actually is unitary. This is actually a bit of a shocker, but it is what it is. In infinities, things are a bit more complicated. I'm not going to go into that, but it has to do with the fact that you have a confluent equation. So you have to do some funny business with this operator so that they behave like what you expect in a confluent differential equation. Right. So, okay, so good, nice. Everybody likes mathematics. Actually, not everybody, I know, from what I hear in this Pingo Doce, right? You should recycle because it doesn't need mathematics. But what is it from our perspective? What is for the problem that we're trying to solve? Well, as it turns out, you can solve this kind of Sturm-Liouville problems that I showed you using this knowledge of these monodromy parameters. How does that work? Well, for the angular equation, it's a simple matter of having these parameters that are associated to the south and north pole somehow coincide with this double monodromy. So we call this usually additive monodromy. You go around the north pole, you pick up a phase, and you go around the south pole, you pick another phase. And the solution will be well behaved at infinity, well behaved of both of them. If you go around both of them, the phase that you pick up is just a sum of them. Up to an integer, because of course, since it's a phase, it's defined up to an integer. My parameterization has to be an even integer. And now you can expand. I mean, you can use the expansion that I show you using this f function, implicit function. And you see that this coincides, this number here coincides with the usual definition of angular momentum variable if you choose this integer to be L plus 1. This is well and nice, but the radial equation, this is a bit of a shocker, also can be solved using this parameter. This is actually a bit more complicated, but you can work it out. So you have that the eta parameter that I described to you is related to the sigma parameter of the string of sines. And this is my way of translating that the function is purely outgoing at infinity and purely ingoing at the outer horizon. So whenever sigma satisfies this, then I have a quasi-normal mode. Okay, so now it's the time to wake up. And my 15 minutes are up. If you didn't understand any of that's okay. I didn't understand either the first time. What I want to sum up this part of the talk is that these monodromy parameters that I want you to that basically define how the solution of these equations behave in the complex plane. They should be a 2 here. Sorry. They dictate the global aspects of this solution. So I know how the solution behave at infinity, given how they behave at 0, if I know how to compute this. Actually, people at CENTRA, they actually computed the actual, what's called the connection coefficients. So this is the usual scattering problem. You have a solution that's purely ingoing at the horizon, and this will be a sum of solutions that are outgoing and ingoing at infinity. And you can read from this the coefficients you can read from this what is called the connection coefficients can give you exactly what you need, the reflection and the transmission amplitudes. Moreover, and I guess this is the part where it begins to get interesting again, is that you can compute these parameters efficiently. So I mean that there is a polynomial time involved in here. I can compute them. It would be nice, perhaps, for mathematicians, but perhaps not so useful if I could only compute that using in exponential time. But this actually can be computed in polynomial time. You can make sense, try to make sense of the CFT. The little string theorist that still lives in me cannot help but begin trying to get these connections made. First of all, this has nothing to do with this old ways of trying to define holography in symptotically flat spaces. Nothing to do with that. However, nonetheless, you can try to make sense out of the CFT. Funny business. Just 2 pieces of information. There is a CFT for each coordinate, first of all. One for r, one for theta, and in some sense there is one for t and one for phi as well. The CFTs are unitary, a bit of a shocker. And furthermore, they are in thermodynamic equilibrium. I will be happy to discuss this with you if you are. You can use this tool to compute quasi-normal modes of black holes. I've been doing that for some years now, but hopefully some people will be interested in doing that. Boolean is doing that as well for all the black holes. But there are other uses for this. You can, as I told you, you can compute scattering coefficients. You can compute gray body factors. I mean, sometimes they are not the same. Log numbers and so on and so forth. And the point here is that this is the problem I should probably emphasize before. Remember that I told you that you have this small t expansion. Using the CFT method, you can also derive a large t expansion, and furthermore, you can relate the 2 expansions. So you can basically cover all parameter space using this method. This is the good thing about this. As I understand, the lever method breaks down as you come close to the extremality. This doesn't have any of this problem. You can always switch between the 2 and look what's best for you. The price to pay is that you have to compute this new parameter sigma. Sometimes it's given to you by the boundary conditions, but if you study scattering coefficients, you have to compute it explicitly. Okay, so now please wake up. I can't resume talking about physics. Well, sort of. If you work this machinery in the angular for the angular eigenvalue problem, you're going to find the usual expansions for the standard harmonics. Just that in this case, since you have mass, the parameter of expansion is not a omega, but rather this. This is actually, I mean, this is known, right? I mean, you can open up an IST and you find this stuff. There is just a way to check that our formulas are correct. And you can also derive a large frequency expansion. These are basically used, you can basically do that using WKB methods, although you probably will run out of patience before you get to the third term. In this way, you can do that algebraically up to the order that you want. I mean, one of the referees went to order 150. I guess he had too much time in his hand. But this is basically, I mean, there is nothing really exciting here. There's no new results. Then you turn to the radial equation. Well, radial equation, you can define dimensionless variables to parameterize the system. And since once you define these dimensionless variables, you find that there are no natural small parameters. Since there are no natural small parameters, you have to solve this numerically. There is no way around that. I mean, you cannot find a suitable expansion point. You can find some asymptotic behavior and so on and so forth, but generically you have to solve this numerically. Anyway, then you can actually look at the frequency numerically as a function of the mass and the angular momentum. Usually, the spectrum here, they differentiate between these non-co-rotating modes, so the modes which have the azimuthal, the angular eigenvalue different than the L, and these have a smooth limit in the extremal point. These are usually called damped modes because the imaginary part, as you can see here, does not go to zero. It's a small number, but not zero, as you come close to the extremal point. And here you can see that this actually, increases, right? So it becomes longest lived as you increase the mass. There's nothing, here also there's no surprises. This is all known in the literature. When you come to this, to the co-rotating modes, and this is basically what I'm going to spend the rest of the seminar, there are these so-called zero damped modes or undamped modes. I don't know who to talk to say which is which, but which is the right technology. But these modes, they have the property that the imaginary part goes to zero as you go to the extremal point. So you can see here, the real part also goes to m/2. You can see here this is L equals 2. So you see here that the real part increases up to 1 as you come close to the extremal point, and the imaginary part goes very sharply actually to 0 in the extremal point. And you have this smooth change of behavior with the mass, apparently smooth. And you can do this. I guess this is also known. I mean, since the 80s. Perhaps the new thing that I could tell you that we've done is that you can follow these modes adiabatically from the Schwarzschild modes up to the extremal limit. You don't need to jump in there. There are some asymptotic formulas in this case for these modes only. You can give it by this. This is also known, although the prefactor here is a bit different from what was known in the literature. Again, nothing new, no new phenomenon. However, if you zoom out the region here near the extremal limit for the L equals 1 mode, you see a change in behavior. What's going on? Well, you can see that if the mass of the field is low enough, yes, the mode is going to come to this undamped mode, and the asymptotic value will be L/2. In this case, it's a half. See that? But if the mass is large enough, you see that it begins not to appear to have a limit where the frequency goes to L/2. If you follow through to the imaginary part, something even more dramatic happens. If the mass is low enough, the imaginary part goes to 0. This is 0. But if the mass is increasing past a certain value, it does not. So you have a transition between undamped modes to damped modes as you tune the mass. This happens very close to the near extremal region. If you zoom in really well, you see that there is a bifurcation. So what does that mean? It means that if you, in this case, I'm plotting the real part as a function of the mass, and I'm increasing the angular momentum. I'm sorry, yeah, I'm increasing the angular momentum. I begin with the mode that's on there, and as I increase it, it falls to that's actually this is the other way around. Yeah, of course. No, this is not. Sorry, my mistake. These are angular momentum below some certain value, and then the modes they have this smooth property. But if you increase the angular momentum past the specific value, since rather close to the extremal point, they will jump. In this case, there will be some almost discontinuous jump between the modes that goes that increase here and increase that. Well, you may ask, okay, is this discontinuous? And I tell you, not really, because the method that we consider, it's also very precise. We can usually get, well, at least 9 or 10 decimal places. And even if you reduce your step to 10 to the minus 7 here, you still see this bifurcation. Here you see also that the imaginary part also jumps from signs here. Yeah, they jump from this behavior and goes smoothly, or increase this case smoothly with the mass, to a point where it also bifurcates following this flat line. It's in order to see this point, it's actually more convenient to use this variable sigma that's related to the angular velocity, like so. And you see that this is really like a choosing roots of the square root. Some point you get to the positive side, and the other point you get to the negative. Again, I have to stress, this is the step that you use to derive this, and this derivation is numerical. It's much, much smaller than the structures you see. It's 10 to the minus 6 or 10 to the minus 7 here. And still, if you change the values of the parameters slightly, you either follow the path that's going upwards or the one that goes downwards. You can also see that this, if you study now the excited states, you see that's also something funny happening. Exactly at the same point, it seems that the what you would call the fundamental mode in Schwarzschild, and you follow it through up to near this extremal point, changes places with the first overtone. So as you increase the angular momentum, the fundamental mode of Schwarzschild becomes more attenuated than the first overtone. So they change places. So there is some sort of behavior in which the longest living mode is always the same mode as you follow through the Schwarzschild case. But as you go through this point, this bifurcation point, the first overtone becomes longest living. And this overtaking happens in a place that's suspiciously close to the bifurcation point. So we can study what's going on. If we plot both of them, you can actually see that they change places. This, I'm going to get this backwards. Yeah, this is the n equals 0. So this is the fundamental mode according to Schwarzschild. And if this is slightly, yeah, if this is slightly above the bifurcation point, then it has this behavior. If it's slightly below, you cannot see from here because the picture is very bad. It goes back towards this point. And what I'm drawing in solid lines is the n equals 1 mode. And you see that n equals 1 mode has this behavior. If I increase this, I have this the behavior for n equals 0 and this behavior for the change place. Here you see that you have this region here where n equals 1 has a smaller imaginary part than the smaller in absolute value, of course, than the fundamental. Okay. So, okay, what's going on then at that point? Well, that point is a point where the imaginary part of the fundamental mode, according to Schwarzschild, is the same as the imaginary part of the first overtone. you can follow through a line in parameter space in which the imaginary parts of both of them are the same. So they are equally lived. This line goes up to the extremal point. And you see that this is also, it's already very close to the extremal point. It's already 10 to the minus 3 to the extremal point. Although the method is quite, it's quite accurate, in order to see this effect, you have to really, really go close to the extremal point. Well, if you try to understand this in a more qualitative term, then I have a nice picture for you. I hope that, more. It's been known for some time that if the mass of the field is large enough, the imaginary part is going to be of the fundamental mode is going to be positive. So these modes are unstable. This is known for 20 years. So there's a line here, the green line, where the imaginary part of this fundamental mode is 0. What we find, and this is of course not to scale, is that there is a critical point in which the imaginary line of the fundamental mode is equal to the imaginary part of the first overtone. So the question now, I guess the natural question that you have is, okay, what happens if I try to go beyond this point? Well, if you go beyond this point, there is a funny thing in which now there's a line where the real part of the fundamental mode and the real part of the first overtone, they are the same, but the imaginary parts are different. So this point marks this change of behavior. Okay, I guess that the physical question now is that, given that I have this parameter space, what is the longest lived mode? If I follow adiabatically the fundamental mode past this point, it's not the fundamental mode anymore. So it's not the longest lived mode anymore. If I go around this point now towards this other path, what happens? There is no discontinuity here. The fundamental mode is always the fundamental. So what is going on? Well, we can actually do the exercise. So the way we do this is that we find a root, we find a quasi-normal mode, and then we change the parameters adiabatically over parameter space and try to see where the mode is going to end up. If you follow this procedure, this path, this step that you use, that numerically is very small, like 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. If you follow this path A to B, you can start with this point A here, where it's supposed to be to the left of this coexistence curve, and B below this point, and C and D to the right, and D above the point. Nice. I guess I didn't tell you exactly what the coordinates of that point is, but I'm going to get them. Anyway, if you follow through, so you have here, this is the fundamental longest lived mode, and this is the first overtone. If you follow this mode adiabatically through this path, A to D, you're going to find that this mode, as it gets to this point here, D, has this value for the imaginary part. If you follow through this, the first overtone, you see that it becomes actually the longest lived. Follow this path. If you go now round this exceptional point, you see that the fundamental mode maps to the longest lived mode, as you would expect, and the first overtone maps to this first overtone to the more excited modes. It's unexpected. So what does that mean? It means that they'll have a hysteresis around this path. If you take these two states and you follow through adiabatically this path here around, you compass this except at this point, then the two states they change one to the other. And this changes adiabatically. If this system was a unitary system, quantum mechanical unitary system, we would call this a Berry phase. But the system is not. The system is not unitary due to this imaginary terms in the effective potential. So this is what it is called in the literature of quantum mechanics of open systems a exceptional point. So the bifurcation point is actually an exceptional point. And people are interested in exceptional points in quantum mechanics of open systems because they want to build quantum NOT gates or quantum computers or what have you. So you can think of this as the least practical quantum NOT gate ever. The upside is that you can have a coherence time of hours because these modes are long-lived. So just take a Sagittarius A star and it gets 3 hours coherence time. These people in condensed matter, they'll be crazy about this. If you follow through the analysis, you'll see that the space of quasi-normal modes at this point has a double-sheeted cover, just like the square root. If you remember your complex analysis, you go round, you change this sign, so you change one normal mode to the other. If you go round twice, everything stays the same. So in a sense, there's manifold frequencies to sheeted. I guess this is the, yeah. So before the comments, let me just tell you that this exceptional point is a very specific point in the parameter space. So the angular momentum is given by this. And as far as you know, these are indeed 8 decimal places. And the mass, I hope I wrote it there. Perhaps it's behind the black box. Anyway, it doesn't really matter. I can read it up afterwards. But if you remember your thermodynamics, and I'm in a condensed matter department, remember that. There is something that you study in high school, well, in college thermodynamics. It's called a phase diagram, and people usually talk about the phase diagram of water. And you have a liquid phase and a gas phase, and between the liquid and the gas phase, there is a phase transition. There's a latent heat and storm. And this line ends, the coexistence line ends at a triple point. And the funny business is that if you follow through the state here, past this point, the system may become supercritical. What does that mean? It means that the most entropic or the least free energy state, which is liquid below the line, as you follow through, it becomes unstable. And if you shake it or give it any kind of perturbation, it decays back to the lowest energy, the free energy mode, which is the gas state. Please don't do this, but this is something you can do with the microwave. However, if you go around the triple point, you'll get from liquid phase to gas phase without any discontinuity. The system will just continuously go to one to the other. And this is what is called in thermodynamics a crossover. And this is exactly what's happening here. In a sense, yes, because free energy, I mean, if you have an integrable system, free energy is also written as some eigenvalue problem, and you sort the eigenvalue problems, in this case, for the value, not for the imaginary part. But apart from this technical thing, it's basically the same interpretation. So as far as I understand, and Mauricio, my co-authors, also agree with me, this is the first time such a point has been seen thermodynamic, well, in this case, in the gravitational setting. Unlike the usual quantum knot gates that people model in quantum computing, sort of, I mean, I could get good grants if I wrote them. This is also a system that can derive from first principles. There is a Lagrangian, there is some setting, some state in the system, black hole with some mass, you go forward, crank the machine, you derive liquid. Usually the system is modeled by some effective Hamiltonian that incorporates this the interaction of the quantum system with the environment, and that's why the Hamiltonians that we find, they are non-unitary. Our Hamiltonian is non-unitary by default. It's just the case that unitarity is not compatible with the separation. So from this point of view, this is also nice because we see the same phenomenon. So, okay, to sum up, because, there's the nice thermodynamic analog for what's going on. We find the exceptional point. We have this coexistence, sort of coexistence line where the first overtone and the fundamental mode according to Schwarzschild, they have the same imaginary part. Like in water, I don't know, perhaps there is some some contribution that this has to give to the issue of the stability of the system. I would like to say some words about that. These, as I told you, these exceptional points are usually associated with quantum mechanics of open system. This is not this the system here, although it's unitary, it's not compatible with separation of variables. So you have the same sort of symmetry breakage that leads to the exceptional points there. This should be a generic feature for all the black hole systems. Although, well, my colleagues they have found in some other setting, but I'm pretty sure this is more universal. I told you about CFT. I don't need to tell you anymore. If you want to discuss, that's fine. And the point here, perhaps, is that if you want to be serious about the global structure of these quasi-normal modes, you have to learn a little bit more about these new special functions. Okay, that's it. Thank you.
If you enjoyed the video, like and subscribe.